The best way to solve a ramps and pulleys question is to treat the two masses as if they're one big block. Now that makes sense because if each block is going to, they're basically going to accelerate together. The reason being is if M1 accelerates too much compared to M2, then that will increase the tension between them, and that will pull M2 along with a greater force and increase its acceleration. And then if M2 has too big an acceleration, well then the tension force will go down, the rope will go slack, and that will decrease the acceleration. So there's always this kind of interplay between them. So we're going to assume that the tension is a constant and that the two masses move together with the same acceleration. So we can treat them as a big block. I'll make this a red block. So I'm going to put my free body diagram over here, and I'm going to say the mass of this new block is the total mass of M1 plus M2. Now, what I'm doing is I'm basically turning the ramp into a flat surface as well. I'm doing two things. I'm grouping the two masses together, and I'm also flattening this ramp out. And the reason why I'm doing that is to make the calculations a lot simpler. So if we look at the forces that are acting on these two blocks, we have a force of gravity, or a component of gravity, acting parallel to the ramp. And I like to call that force of gravity parallel. There is a normal force here that is equivalent to the force of gravity perpendicular. So these two magnitudes of these forces here are not mg, which would be straight down. They are smaller than mg. And as the ramp tilts up, then this force increases and becomes closer to mg, and this one decreases. Now there's also a force of friction acting on this block. And similarly, there's a force of friction acting on this block. And we'll complete the force with a normal force up like this. So I guess I can include the force of gravity on this guy. And there is a force of gravity down here, but I won't draw that in for clarity. Now, the force of gravity, there is a component going along here, which is equivalent to this guy. So this is technically not the force of gravity parallel because it's going kind of an upward direction. But this is the normal force because it's perpendicular to the ramp. Okay, so because I've grouped these together, what I'm going to do is I'm going to first I'm going to assign a direction, which I think everything is going to go in. So I think this thing is going to move in a counterclockwise direction. And then, because I'm straightening this out, then going to the left, the only force going to the left that's kind of pushing everything along, so going along like this, is the force of gravity acting on block 1 that's parallel to the ramp. This is the driving force. Every other force is holding it back, is hindering it from accelerating counterclockwise. So the three forces of interest here are the force of friction acting on block 1, the force of friction acting on block 2, and actually there's only two forces, so we'll ignore that. Okay, so after we've done our free body diagram, the next step is to make an F-net statement. Now remember, our goal is to find acceleration, so that's why this is a useful statement to make, because when we expand on this, we'll get the total mass, which is m1 plus m2, multiplied by the acceleration of both masses. So this is ultimately what we want. So our F-net, we're going to make things going left, we'll make them positive, because that seems to be going along the direction that we think this is going to be accelerating in. So everything that's going in a counterclockwise direction will be positive. So the only positive force here is the force of gravity along the ramp, and the other two forces are going in the opposite direction, so they're negative. So now we're going to expand on these based on the idea that this is a component, FG parallel is a component of gravity, and FG perpendicular is a component of gravity. So the first thing we're going to do is FG parallel is equal to M1, because the force of gravity is pulling on M1, which is accelerating the system to the left. There is a force of gravity on M2, but it's not helping to accelerate this thing counterclockwise. So this is the accelerating force right here. So that's equal to M1G sine, and our angle here is 50 degrees. So that's 50 degrees. Now for our force of friction is equal to mu Fn. And in this case, our Fn is on an angle. So it's going to be equivalent to this FG perpendicular thing. And then over here, so I'll put a little 1 to indicate that it's mass 1. Over here I have mu Fn on mass 2. So let's expand the force of friction terms a little bit more. So what does this look like? Well, we have Fn is equal to this, because it's not straight up, so it's not just mg, but a component of mg, specifically mg cos 50. And then over here, well, the normal force is straight up, so it's equal to Fg for mass 2, or sorry, m2g. So to calculate A, we'll divide both sides by mt. So that's m1 and that's all over mt. And then we can do our substitutions now. M1 is equal to 100. G is 9.8. Sine of 50. Mu is 0.1 times 100 times 9.8 cos 50 minus 0.175 times 9.8. And then you divide that by 175. And that gives you A is equal to 3.51 meters per second squared counterclockwise.